Okay, let's have a look at the falling film reactor in detail. So let's consider a vertical tube length. This is the vertical tube and it has length term L and the diameter, we term it as D naught. And the liquid admitted, either the liquid admitted at the top such that it forms a falling film which will coat the wall tube. Okay. Kemudian it says here the gas is added. It's either into the top, kalau dari atas kita panggil dia co-current because it is the same flow with direction flow with liquid, or into the bottom, which is we call it as counter current, and yang ini kita panggil wetted wall column. So we assume the liquid falls with a constant average velocity. Term dia kita panggil U, which is L as liquid, and forms a liquid film of thickness, in which the liquid film thickness kita kira sebab since the diameter here is D naught, so maksudnya kita ambil dengan outer diameter. So radius dia of course R naught. Jadi kalau kita ambil the distance from center to the interfacial area here, the interfacial line here, ini kita panggil dia Ri, radius internal, sebab kita boleh cari thickness of the film over here. Okay, and then what we can assume is the liquid film thickness is constant, and then the cross section occupied the gas is also constant. So velocity of the gas as this term Ug, and it is dependent of position Z. And another assumption, if the density of gas is constant. So ini illustration dari jarak dekat. Okay, contoh yang ini species A dalam bentuk gas. Yang ini liquid, species B dalam bentuk liquid. Okay, katalah reactant A ni, it goes through this vertical column, but it of course it will have contact with liquid B ni, so akan berlaku reaction dan terhasillah produk C. Right, in terms of how to find the dimension, so dari sini ke sini R0. Okay, sorry, dari sini ke sini so dari sini ke sini adalah Ri. So ini adalah thickness of the liquid. So secara teori, gas that occupy a cross-sectional area, ini dia pi Ri kuasa 2. Sebab ni adalah sphere kan, sphere punya cara nak dapatkan area tu. Sebab katalah vertical tube kan. Okay. And then the liquid that occupy a cross-sectional area, sebab liquid, so dia dekat area sini saja. Bermakna the liquid pula pi darab R0 kuasa 2 tolak Ri kuasa 2. So this is the thickness. The volumes occupied by the gas, so volume occupied by phases. So kalau untuk liquid, the liquid that occupy cross-sectional area darab L. So terjadilah volume. And for gas, this one is the gas that occupy cross-sectional area ni darab L juga. Okay, so dapatlah volume gas tersebut. So in order to calculate the residence times for each phase, tau untuk L, kita boleh guna length divide by average velocity, ataupun kalau diberi volume liquid, boleh dibagikan dengan volumetric liquid, ataupun kalau diberi in terms of radius and length, you boleh kira dengan cara equation ini. So mana-mana equation you boleh try. So tau gas pula, this is the theory. Length of the tube divided by average velocity of gas, kemudian ataupun volume of gas divided by volumetric of gas, ataupun the volume you kira dari segi pi darab r radius kuasa 2 darab length divided by volumetric gas. Okay, so consider this reaction untuk dalam falling film reactor. For example, reactant A, species A in gas phase. Okay, kita melalui sini. And it will react with species B in liquid phase. So akan ada reaction lah, which is A boleh pergi ke B macam tu. And so terhasillah C, which is C in gas phase, and also terhasil D, which is D is in liquid phase, for example. Assumptions that can be made here, for example, reactions are irreversible, products can easily escape from phases, and then the reaction occurs only in the liquid phase, so there is no reaction in gas phase, for example. So rate equation for this reaction is, you boleh kira reaction rate dekat liquid equals to K constant liquid times CA, okay, times CB liquid, semua liquid lah, and RG ni equals to 0 because there is no reaction at gas phase. Okay, previously slide sebelum I tunjuk kat you macam mana nak cari reaction rate at liquid dan reaction rate at gas phase. So dua-dua ni adalah kita panggil pseudo homogeneous rate. Tapi kita kena ambil kira the mass transfer rate juga. Okay, jadi kalau nak kira the mass transfer rate dengan mengambil kira equilibrium gradient. So ini dia punya ni lah equation kita dah tunjuk sebelum ni, yang mana area of interface kita boleh kira guna equation this theory. Tak sama dengan cross sectional. Cross sectional is the cross sectional area. Okay, cross sectional yang macam tu. This is cross sectional area which is occupied by gas, for example. Tapi kalau area of interface ni yang sepanjang ni. Okay, so ini adalah L. So kita darabkan dengan 2 pi Ri. Okay, sebab kalau dibentangkan dia akan jadi panjang begitulah. So ini adalah 2 pi Ri dia. Okay. So mass balance for the phases, kalau can you recall in previous slide? Okay, kalau untuk phase gas, phase liquid for example, so katalah untuk species A at gas phase, tapi disebabkan reaction rate at gas phases is no reaction, so kita letak dia as 0. Yang ini adalah the mass transfer rate, which is kalau previous slide dia bersama dengan A divide by volume kan. So you kena tengok balik previous slide. Okay, so K CJ get CA at G. Okay, gradient dia CA L. So yang A ni, this is the area of interface. So boleh kira dengan cara ni lah. Yang ni masukkan, right, divide by the volume. So dapat yang ini okay, kemudian untuk liquid, so kita dah define the reaction at liquid. So and define untuk area of interface for liquid, which is just the same. And this is the volume of liquid, and this is the mass transfer rate. So this is something to ponder for falling film reactor. Reactor volume is proportional to R0 squared, while the surface area for mass transfer is proportional to R. The falling film column will be less efficient for larger reactor size. And then the mass transfer coefficient is usually much lower in liquid phase. Therefore, CA in liquid phase is a function of R, which is distance from the wall to interface.